just goes with what the last project bounds were. So see, I've got a blank page right now. If I go into the, let me change the name of this to activity 2. It remembers sort of where I was last time. It'll go right to the Darnell Road area when I open up that little mapping tool once it starts responding. There it is. See, it just sort of remembers where it was last time, and so that then it fills in the project bounds. All right, so I'm going to go with the DEM, the NLCD, and then Surgo. Surgo is a higher resolution data set than StatsGo. StatsGo has very few polygons in an area, a watershed area the size that we're working in. Let me see if I already have the land use. Maybe I'll save myself the trouble of downloading that again. Or I mean the soil type. Yeah, I'm not going to download the soil again. It takes too long. Oops. Download data. Okay, so remember, you once you get the DEM, then you want to calculate topaz, compute topaz. It begins and ends, and then you find the location you want to drop the outlet, and remind me, it's right over here, I think. I'll add the image. Darnell. I'm blind. Where's Darnell at? Oh, there it is. Okay, yeah. All right, here's the crossing. Okay, so drop the outlet here. Have it delineate. Is it about have I got the right watershed, about 1.6 square miles? Is that what everybody else has? 1.8? I may not have had the, there's that one extra branch of it that is easy to miss. If you create a watershed, it's actually quite a huge hassle to delete one again. I'm going to select this outlet and delete it, and then turn the resolution of the stream accumulation up so I have less of an upstream area that'll show more of these little networks. I think what I need to do is actually have both sides of this branch, and so I'm going to drop the outlet. Yeah, so once I have this other branch coming in, if I get it after it joins, then I can get it to delineate, and it'll, I think, be the 1.8. It's giving me this message that it's going to delete all the previous watershed boundaries that I defined, and that's actually what I want it to do. Yeah, it's a little bit screwed up here because it's seeing that old node. So unfortunately, you have to start from scratch a lot. Or I guess I had saved my work. I'll just open up that activity 2 file. Not a lot there. topaz. And my mistake previously was not getting that other boundary, so I want to get both branches as they meet in. I'll add the image file so that I get freeway. All right, so I want to put the outlet after they come together and then delineate. All right, 1.8, yeah, that's more like it. I'm going to add the land cover, or the soil type data. Remember that when we add it externally, it's the file that's the biggest of all of them. And then I'm going to have to join the NRCS database. And if I don't do that, if I don't join NRCS, it's not possible to map it into the new soil type coverage the way that we need. Remember, we're just going to take selected polygons from this overall shape file of the entire county's soil data, and we're going to put those selected polygons into the soil type coverage. But if we don't have the A, B, C, or D hydrologic soil group defined, then we won't be able to calculate the curve number. And so if you right-click on here, there is, I may not have seen that as, yeah, I have to delete that and add it again. Let's see. What did I do before? GIS or shapefile? Add GIS. There it is. Join NRCS data. Join hydrologic soil group. And now I can select some of those polygons that are in the zone that I'm interested in, map them to the soil type coverage, and scroll over to make sure that it's matching the SCS soil type as the hydrologic soil group. And then once that's mapped, I don't need this file anymore. I don't need the shape file there. It just is going to slow down how long it takes to open up the model. After this is finished thinking, I'll save my work. And then remember, the last thing we did last time in class was calculated the curve number. And to calculate the curve number, you have to have the watershed boundary defined. So you have to have delineated the watershed, and it's I'll turn off the soil type coverage just because it's sort of slowing down how quickly things display. You've got to have an area, so it needs to know what the watershed boundary is. That's one of the necessary components to calculate the curve number. Another is that you have to have this land use grid. It doesn't have to be turned on, but it has to be in the project. And then you also have to have the soil type data. You have to have those polygons not turned on, but present. And so in the hydrologic modeling module, there is a calculator, compute GIS attributes, and then through the process of importing the table that I emailed, and it's posted on MU Online, it is that table. I think I maybe put it on my desktop. There it is, curve number. So this is where it defines different land use IDs and different soil groups, and it can do the calculation and finds that the curve number is 71. So that's a little bit different than the curve number that I emailed to you yesterday. That may be that the watershed boundaries are slightly different. But what we're going to focus on today is setting up a HEC-1 model. So is everybody at this point where you've got the curve number calculated for your watershed? Now, you may not say all the same display options. It says the area and the curve number. Let me show you how you can define other things. Like on the previous activity, I was going to ask you to fill in the blank on the average slope of the watershed and a few other properties. You can get that info. Go to the drainage module up here at the top, and then select a drainage unit or basin. And if you click on that tool, then it allows you to pull up some properties. You've selected a basin and it tells you a lot of information about that basin. For example, the area, which was already displayed, and so was the curve number. But here are some geometric parameters, like the maximum flow distance, MFD, the basin length along the main channel from the outlet, to upstream boundary. All right, or the basin slope, the BS, 22% basin slope, it's really steep, watershed. Average overland flow distance. This is kind of an interesting property because it tells you how long water is going to flow over the land before it gets into a channel on average. So there's a lot of statistics here, that maximum flow length, a lot of statistics that go into some of the different formulas that are used to calculate time of concentration. You know, we talked about the SCS formula for calculating time of concentration, but there are a lot of other ones. There's the kinematic wave, Kirby, FAA. There are dozens and dozens of different formulas that use various geometric parameters to calculate times of concentration. So you can get a lot of that information here in this window. And if you want to display it on the screen, then you can go into the display properties, display options, which looks like a little computer screen, or display options. So bring that up, and then in the drainage data tab over here, different windows pop up in this screen depending on what tab you have selected. But under drainage data, you can select which of the basin properties you want to show for the watershed. So if I wanted to have the basin slope and the perimeter listed, I can select whatever I'd like to see and then click OK, and it brings them up on the screen there. And remember that this tool here, frame, will just make it fill the entire window, whatever is actually on screen at the moment. So if I frame, it'll zoom in as much as it can. So is everybody able to adjust which parameters it summarizes on the screen there? $317 for what? Yeah, I wonder what units you're in. Yeah, you can sometimes specify different flow units. Sorry, meters. I would guess it's probably a units issue. Or the flow accumulation. Let's see. If you change the upstream area here, like that, to 0.1, then it might change that calculation. So, and then I don't know if you have to redelineate or if it would update that altogether. I don't know, but I'm not sure. And there are a couple of possibilities. It could be units, or it could be, if you redelineate now, it may update the... No, it stayed the same, huh? I don't know. That's an interesting one.
Where can I go to make a show less of the
You go into the display options, and then up to DEM data, and minimum accumulation for display. You could be like 4 acres or something like that. Did it change it? All right. Turn off the flow accumulation and stream. You've got a lot of extra options on. Click OK. Let's see. what it's done is it's actually made arcs out of the flow accumulation. So it's showing the lines and not necessarily it's not flow accumulation anymore, but it's actually made lines out of the flow accumulation. Like, it's not a problem, but those aren't just drawn on top of the DEM anymore. Those are actually arcs now. All right, well, let's set up the HEC-1 model. What was it? PUTM XX1? All right.
I have a quick question.
Uh-huh.
I have the card number for this not showed up on here, so how would I like recalculate the card number?
You go into Calculators, Compute JS Attributes, and you have to import that key file that I've provided to you previously.
Just all these things.
The land use is there, and you've got a soil type. So, yeah, all you need to do is import that key file, and then click OK. Mm-hmm. Yeah, there it is. If you, by the way, if you have previously calculated the curve number and maybe you know the curve number for this watershed, but you don't want to go through the process of recalculating it, you just want to enter it, that is possible in the modeling process that we're going to do. So let's start off by opening the hydrologic modeling wizard, the hat with the roller skates here. Go down to, let's see, select model, and we're going to do HEC-1. There's some other options here, and HEC-HMS would probably be the most popular model today. And the reason why is that the Army Corps of Engineers put out a free preprocessor for it, similar to WMS in a way. What WMS is actually is it's a preprocessor and a post-processor for a variety of models, for all of the models that you see listed here. And so WMS is not, the people at WMS didn't invent HEC-1. HEC-1 is a government model, but what this program WMS does is it gets everything ready so that you can run HEC-1 more easily and more quickly than you'd be able to without a preprocessor. It formats all of the data files, it does calculations to sort of get everything ready. Well, about 5 or 6 years ago, the Army Corps of Engineers put out HEC-HMS, and my feeling is that it doesn't have anywhere near the capacity that WMS does. It doesn't have the ability to calculate curve number based on soil type and land use. It doesn't have the ability to delineate watershed boundaries with the DEM. It lacks a lot of the same punch that WMS does. But the underlying model is very similar to HEC-1. Like if you run a simulation by HEC-1 and you run the same assumptions in HEC-HMS, you'll end up with hydraulically the same answer, but HEC-HMS has some routing options that aren't available in HEC-1. And so the bottom line is that if you go into industry and you end up doing watershed modeling, you'd probably learn HEC-HMS just because it has more options available. But you don't get any different answer with HEC-1 versus HEC-HMS. It's built on the same idea of curve numbers and time of concentration and using unit hydrographs and so on. GSSHA is sort of like the next generation of hydrologic modeling, and it's a gridded hydrologic model where instead of lumping all the parameters for a watershed together, it breaks a watershed up into elements, and so that you're calculating the infiltration and the runoff and all of the hydrologic properties for just segments of a watershed at a time. And so it's sort of, the analogy is a little bit like finite element modeling for watersheds. So it's pretty sophisticated. TR20 and TR55, on the other hand, are not sophisticated at all. They're far more simple models than HEC-1. And with both of these models, you calculate a curve number, but then the runoff is just based on a very simple hydrograph, and it doesn't break the storm up into lots of small pieces. It runs the entire storm event in a single calculation increment, whereas HEC-1, what it does is it steps through a storm in 10 or 15-minute increments, whatever you specify. And so TR20 and TR55 lump the time parameter together, whereas all of the previous models that I've mentioned to you handle them separately. NSS is called National Streamflow Statistics, and it's a little bit like the maximum possible flow that could come out of a watershed. Remember, we talked about the idea that, you know, over the course of hundreds or even thousands of years, there's some storm that's at the outer limit of possibility. You know, how much water could possibly come from the sky at a certain time for a certain watershed area, and that's what National Streamflow Statistics is used for, is that worst case scenario that goes well beyond the 100-year storm. And of course, you already know the rational method, Q equals CIA. The rest of these, OC stands for Orange County. They have some specific hydrologic models that have been included in WMS, and MODRAT, I don't remember what MODRAT is, but a lot of WMS's functionality has been put together for Maricopa County in Arizona, and I don't remember whether MODRAT is something that they put out. MODRAT probably stands for Modified Rational Method. But what we'll focus on today is HEC-1. It's a very powerful watershed model. It's what they use at the hydraulic and drainage section at the Division of Highways. They've started using HEC-1 and WMS. So if you click on HEC-1 and initialize model data, what it does is it'll copy over everything you've calculated so far into the HEC-1 model. So that means it's going to calculate the basin area, it's going to copy over the curve number and everything else that's already defined into the blanks that exist in the HEC-1 model. You click Next, it brings you into the job control. This is where you can say how long you want the simulation to be. And so on the handout I've given you, we're going to set it to be the 1st of January 2013, starting the simulation at 1 p.m. What this would allow you to do is to put in the actual hydrograph, the actual hydrograph for a storm that you know. You can go back to a historic date. We're going to go to 1/3 at 8 p.m. and calculate in 15-minute increments. It's going to calculate a hydrograph ordinate every 15 minutes during the more than 48 hours that we've got specified. Was it 45 hours? Okay. Set job control data. And that copies those windows that we've just specified into the job control for HEC-1. HEC-1 was originally written during the Fortran days when they were just getting away from punch cards, and the formatting of the input to the simulation is very specific. Spaces have to be in the right place, and they had really a lot of limitations on how long programs could be, and so they had to have a pretty compact coding system, and all of this sort of user-friendly information that WMS is taking from you is being encoded into that very strange Fortran input language, and I'll show you where we can see some of that in one of the future windows. So I'll move on to next. We've already got land use and soil data figured out. We calculated the curve number with that previously, so we can just skip right through this land use and soil data window. Okay, the next thing, hydrologic computations, is we need to calculate the time of concentration. And we're going to do that by using the basin data. So if you click on this basin data tab, it brings up all the different options for how to calculate either lag time or time of concentration. And if you go through lag time, you'll notice it's got really a lot of different options for calculating lag time. Or time of concentration, you can see that there's a lot of different methods for that. And it tells you down in this window what each of the variables are and what the value is that it knows for the variable of the watershed. We're going to use the lag time SCS method. The SCS method in the formula here looks similar to what you did in the homework. It's that formula where in the denominator it's 1900, the square root of the slope. So it tells you what the formula is it's going to use to calculate the lag time and then what some of the variables are that it's calculated. John, I'm just wondering, what watershed length does it have for you? Because it got that same 13,000 approximately? 11,000? So it's not half of the value. Vimal, how about you? What does your watershed length say? 12,000? All right. Yeah. Okay, so this formula is going to calculate the lag time based on the watershed length, curve number, and the slope. You click, it tells you here that the result of that's going to be 0.66 hours. So OK, and the 0.66 hours is converted. It's found the time of concentration from that. So remember, the time of concentration is 5/3 times the lag time. And so if this is the lag time, 0.66 hours, it automatically converts that to a T sub C. We can click next. And we're going to define precipitation here. We want to get a 3-inch 24-hour storm defined here. So click on Define Precipitation, and then in Edit HEC-1 Parameters, these are actually all of the data points that are being filled in by WMS. And this is what the window looks like. This is the Fortran formatted input file that WMS is going to prepare for HEC-1 to read. You can see that BA 1.8419, that's the basin area in miles. We haven't defined the precipitation yet, so if you click on the precipitation button, we're going to use basin average, meaning that the same amount of precipitation exists over the entire basin. And the precipitation depth we're going to define is 3 inches, and then click on Define Series, and that gives you the choice to select a curve. And the curve, what it shows is basically the how much of the storm happens at what point during the time of the storm. And we're going to do a selected curve, so click on New Curve, and it's a Type 2 24-hour. John? Yeah, we'll go back to that. It's easy to put in again. We'll come back to it. Define the precipitation for now. Can you go into the precipitation? Type 2 is what we've got here in West Virginia. We've looked at maps across the country, how there's different zones in different places. We've got the Type 2. We'll come back to that once we enter in the define precipitation. That one. Yep. It didn't give you the option to say no?
It didn't even tell me what was happening.
Huh?
I never even knew that it was
No. All right, so click OK and OK again. So I think some of you lost your curve number. If you just go into the loss method here, you can type it in again. CRVNBR. Just type in 71.9 or whatever curve number you had before. And then if you need to calculate your time of concentration, then you can go into unit hydrograph method and then SCS dimensionless and then calculate the, let's see, we're doing basin data. And now that you've defined your curve number, you can calculate the lag time SES method. So to those of you who lost your curve number, I guess you lost your curve number and then you lost your computer, right? All right. What about the time of concentration? Yeah, okay, good. All right, so scroll down through here. Back in the olden days, before WMS or other preprocessors, people who wanted to run HEC-1 had to use Notepad or some other text editor to prepare files that looked like this. And if a single space was in the wrong place, then the model didn't run. So it was laborious, and a watershed that we can set up in 15 minutes in WMS would take literally days to prepare. All right, so we can click Done. We've defined the precipitation. Next. Now, this cleanup model thing, I've never done it before. I just actually noticed it for the first time when I was going through the Hydrologic modeling wizard. We can run it, but I don't think it really does anything necessary. Okay. No errors we detected in the HEC-1 model. Done. All right, now we're ready to run the hydrologic model. One little quirk, another quirk of HEC-1 is that sometimes if you've saved your file in a directory that's many subfolders deep, then the program can't go and find your input file. And so you'll notice that I'm running it in C, WMS, activity 2 demo. So it'll be able to go find that no problem. But if I had it in like my documents, school, classes, demos, computer, awesome, WMS, like if I had it in thousands of different subfolders, then chances are good it wouldn't be able to go find that input file that it's going to read when it goes to execute the model. So put it somewhere shallow rather than somewhere deep. And you don't necessarily have to keep any of these output file or solution file. It'll write these files for you, but WMS is actually going to open the output files that it writes, and we can interact with it, with the solution to the model through WMS. Sometimes I'll come back and actually use this output or solution file, but ordinarily I'll just run the simulation and then look at the hydrograph inside of WMS. So click Run Simulation, and it's gone through that 45 hours or whatever, no, 55 hours at 15-minute increments. You close it, finish the wizard, and you'll notice that there's a little hydrograph here. If you double-click on it, it brings up the hydrograph from the storm. Go to that one. And the next one to the right of it. There it is. But it's clean.
So I need to run somewhere.
Yeah.
It's probably not going to find mine.
Let's see. Oh, you got lucky. All right, so close it, finish, and then double-click on that little white icon, and there's your hydrograph.
I'm pretty bad about storing text to hundreds of them.
Yeah?
So
You've got it really specified. It's a double-edged sword. Okay, yeah, click it. Okay, go next. Looks good. We don't need to do anything there. You will have to calculate that though, so using basin data. Define. Precipitation. Selected curve. You do the type 2, 24 hour. Yeah. Run simulation. There it is. All right, so you can close both of those windows and double click on the little white icon that's the hydrograph. Yep. Double click on the little white icon. Either one. There's actually two little hydrographs that it makes. If you noticed, it has the hydrograph for the watershed and the hydrograph at the outlet. In this case, the two are going to be equal, but if you had broken this watershed up into two segments, then you'd have a watershed for maybe one of the segments, for another one, and then at the total outlet. So either of these two is going to look identical. The peak is 374, and you can say here, the peak 374, it's the same. What's the range of peak flow rates that you've got in your models? 389, 374, 245, really? All right, so here's some nice thing about WMS is, remember here is the hydrologic modeling module. This brown icon might be behind the text, so click on it and move it out of the way so that you can actually double click on it. Double click on that little brown icon and it'll bring up the HEC-1 dialog again. Or I guess maybe you can go to HEC-1, edit parameters. Okay, so has everybody got this window open? Go to that one. Yep. Nope. Next one to it. To the right. There it is. Double. Okay, so just like with water gems, where you can simulate by changing something and instantly come up with a new hydrograph, you know, in water gems, here we could say, well, let's say that instead of 3 inches, the precipitation is 3.5. Click OK, done, run simulation, and it will execute it again with the new rainfall amount. And if I double click on the hydrograph, it's got both. It's got the one before in yellow was the 3-inch, and then what's in black was the 3.5-inch. So I can compare how just a ½ inch additional rainfall takes my hydrograph from maybe 350 up to 550 CFS. Taylor.
Can you like import data like with NOAA that have like different intensities or like different distributions based on area? Like is it possible to import data like that and use it for precipitation?
Are you talking about a different curve than type 2 curve?
No, I'm saying if you have like varying rainfall or intensities or precipitation amounts.
Oh yeah, yeah. You don't have to use the this series. You can have a hypothetical storm where there's a lot of different options. So if we go to define series, you could change this distribution if you wanted, or you can bring in like actual gauges. Yeah, through this gauge thing, you can have you could add a gauge and do like a Thiessen weighting automatically. Yeah. Okay, so if we don't want to have too many hydrographs on top of each other, you go to hydrographs, delete all, and that gets rid of the hydrograph because, you know, if you're going to run a lot of simulations, it's easy to forget which one was which. So I just deleted the hydrographs and then I'm opening it up again so that I can maybe change the loss method. What if the curve number was actually 68 instead of the 71? So click OK, done, run simulation, and there's the new one for 68. It brings the hydrograph down from the 550 that it was at for 3.5 inches, now down to about 400 CFS. I've got all this extra time after the storm that's useless. I should maybe trim it down a little bit. My job is too long. So I'm going to delete the hydrograph, delete all, and then go into the job control, HEC-1 job control. And this is where it was saying, the start and the end of the storm. What it did is that translated it into the number of hydrograph ordinates. And so I've got 220 now, maybe 170 is more like it. OK, run, simulation. All right, and now you can see that some of the leftover time at the end of the event has been eliminated. So I'll give you a few minutes to play around with that. Try a variety of different curve numbers and also precipitation amounts. So say CN of 74, 72, 70, and 68. And for all of those do that the precipitation is 3.0 inches. And then for CN of 70, do precipitation of 4 inches, 3.5, and 3.0. And just note the peak, the Q peak for each of those. Just maybe jot it down on the paper there. The way you do it is you double click on that brown square or go to HEC-1, edit parameters. which one? What condition?
Seeing in a 74 with the P of 4.
4?
Yes.
I'm doing the P of 3.
Okay, gotcha. Okay. Oh, what's it?
Let me take a look at something. We'll close this. All right, we will delete the hydrograph, delete all, and double click here to bring up. Look at it. The precipitation is at 3, and you've got type 2 24-hour. That's good. And we'll go to loss method, curve number 74. All right. It might be that it was finding the peak from a previous hydrograph. If we calculate now, run simulation, okay, then open it up. 1,000, yeah, I don't know. It's very strange.
Something set wrong.
Oh,
Something
I
somewhere.
bet it's the time of concentration. Let's go into the unit hydrograph method. Yeah, lag time is 0. So the lag time wasn't defined. We go in here and we'll say it should be the SCS method. Yeah, now it'll work. Now, there's something I should point out, and that is, officially, if you're changing the curve number, remember that the lag time should be different for each one of these simulations. And so if we really wanted to know what the Q peak was going to be for a curve number of 74, what I need to do is open up here, go into unit hydrograph method, compute parameters basin data, and now calculate. If I'm going to do the curve number is 74, I'll go into loss method, say 74, and then I need to recalculate my lag time with the curve number 74. Okay. And so if I don't go through and tell it specifically that to recalculate the lag time based on the updated curve number, then it's going to throw things off just a little bit. So I can delete hydrographs and run simulation. So I'd written 440 when I hadn't recalculated the lag time, but actually if I did recalculate the lag time, it's actually 464 if the lag time is recalculated. But don't, you know, that's an extra step. It takes a little bit more time, but I just wanted to mention it in the interest of completeness. So I think everybody's had a chance to get a feel for how to delete hydrographs, how to change some aspect of the HEC-1 parameters. The main ones that we can change would be like output control, the job control. If we want to change it from 15-minute increments to 10-minute increments, we could do that. And doing that will actually change the peak a little bit. If you go to 10-minute increments, that's reasonable, but for HEC-1, you probably shouldn't have it calculate any steps smaller than 10 minutes because there's some round-off error associated with the way that it defines the precipitation distribution. So I could change the job control, define some precipitation. I'm going to do the 3-inch and set the loss method back down to 70 maybe. Calculate the lag time based on 70, so it recalculates that. Let me show you how to export the hydrograph to Excel. Once you've got a hydrograph, it doesn't matter if it's the same hydrograph as me, just any hydrograph up, like this. I mean, this obviously isn't going to give you the option of changing the line thickness, or if you wanted to have a dashed line instead of this solid line. It doesn't have all the flexibility that Excel does. And so bring up a hydrograph. Double click on it if you've already got one executed. And I'll show you how you can take that hydrograph and import it into Excel. Close, close.
Close?
Yep.
Oh, I'm sorry.
Either, it doesn't matter. Either one's fine.
Okay.
Now click here.
Oh.
The next, nope, next one.
Next one.
Uh-huh.
Oh, okay.
All right.
Ah, okay.
Yep. And double click on it.
Double click on the brush first.
No, on the hydrograph.
Oh, on the hydrograph.
Yep.
Okay.
So it's calculated at several of them
Okay.
on top of each other. All right, so when you've got the hydrograph open, just right-click on it, right-click on that window, and it brings up a series of options. And what we're going to do is export/print. All right? Now it'll let you export this image if you'd want that, but actually we don't. We want the underlying text/data. So select that radio button and then have it write it to a file. So browse to a location that you'll be able to find a little bit later, and I'm going to call it WMS output.txt. It's important that you put the .txt. If it saves it as a .dat, then it won't be as simple to open it with Excel. This is just going to be a tab delimited data file, and Excel will know right what to do with it. So once you've defined the file name, save it, click on export. Now here's another important thing is it's asking, do you want this to be a series of numbers in a column or a series of numbers in many different rows? And many different rows would be ridiculous, but that's the default option. So we have to manually override that and say that, okay, we want it as a table, and we don't want subset/points, we want points/subsets. And what that means is if we had subset/points, then it would put the flow rate and time in 2 rows, but many different columns. Instead, we want this second option here, point/subset. Okay? And then click export. And what we can do is open up Excel and then browse to that file that was just saved. File, open. Oh boy. And you have to have it say all files. Since it's a text file, it won't ordinarily have it. There it is, WMS output.txt. And we want to delimit it with a comma. There it goes. It separated it in a little preview window here. You can see it separated the time and the flow rate fields into different columns. Finish. Okay, good. It doesn't put very meaningful titles on these. I'm just going to delete what it's got for the first one. And this is time in minutes. And this is the flow rate in CFS. So that now you can go through the process of creating your own nice looking chart instead of relying on that chart that was there before. So I could create a graph and add the series that I want to have. So then you can make all the formatting changes you like. You don't actually have to make a chart necessarily. I just wanted to show to you that it's possible to go from the hydrograph WMS calculates into some XY data. Any questions about exporting the hydrograph? All right. The last thing I'm going to show you is the batch simulation. And what we did here would get a little bit tedious if you had to run a model for a series of different storms. Like what if you had to run your model for the 2, 5, 10, 25, 50, 100, and 200-year storm? And what if you had to do that for a high, medium, and low curve number? What if you needed to do it for CN of 68, 70, and 72? So 1, 2, 3, 4, 5, 6, 7 times 3. So you're looking at running it manually 21 times. That'd be miserable. And so there is a way to have it batch calculate all of those options. And I'm going to show you how to set up a batch calculation in WMS. Delete the hydrographs that was there before. And then you go into HEC-1, and there's something called stochastic modeling. Stochastic modeling is a way to have WMS handle uncertainty. Now, we don't actually know for certain that the curve number is 71.8. You know, it calculates it to a high degree of precision, but the underlying data may have some ambiguity in it. And so stochastic modeling allows you to say that there's a range of different values you want to have the program consider. So here, Monte Carlo do 21 simulations and define stochastic model, add variable. Let's actually just start with 7. And the variable that we're going to take a look at first is the precipitation. And then these are the precipitation values. It sort of fills in a variety of values based on a starting value, a minimum, a maximum, the standard deviation. That's for something I'll show you in a minute, but we're going to override that to begin with. No, we want to look at precipitation amounts. All right, what if we wanted to look at a 1.5 inches of precipitation, 2, 2.5, 3, 3.5, 4, 4.5. So we wanted to run the model for all those different precipitation depths. But we didn't want to go in and manually change it a bunch of times. Click Add Variable. And change it from curve number to precipitation. You got the precipitation, or does it say curve number? All right. 1.52, 2.5, 3, 3.5. Okay, there's one more thing that we have to do before this stochastic model will work. We have to go in to HEC-1 and give a precipitation depth of -1 inches. Because there's this flag here. See where it says key -1? That's a trigger to HEC-1 to realize that it needs to look somewhere else for the precipitation. So this is like a separate precipitation instructions. And so click OK here, but then double-click on this brown square to bring up the HEC-1 parameters. And for precipitation, we're going to say average precipitation is -1 inches. And that's the indicator to HEC-1 to look in a separate precipitation file instead of just using this one there. So OK, and done. So all the other parameters stay the same. The loss method, we're going to do this for a curve number of 70. And the unit hydrograph, I can compute that again just to make sure that it's based on the 70. Okay, so I've got my time of concentration. And you'll notice in here, precipitation, -1. All right, good. So has everybody got the precipitation defined under stochastic modeling? Okay, in that case, once it's ready to go, then you say run stochastic model and just OK. And it goes through and it runs it several times. You can see in the window here it's simulation 4, simulation 5, simulation 6. And then when it's finished, you close it, and the hydrograph that appears has all 7 of those hydrographs. If my hydrograph will show up. I don't know why I'm not seeing it. There it is. So those are all the hydrographs for the variety of different rainfall amounts. And you can probably guess which one of them is 4.5 inches and which one of them was 1.5 inches. And we could do the same thing of exporting all of those into Excel. If you right-click and tell it to export, then each one of the precipitation depths would have its own column. So that's stochastic modeling. What stochastic modeling is really for, besides rainfall amounts that you actually know you want to simulate it at, is that you can tell it that you want it to do both. Simultaneously have a variety of different precipitation amounts and a variety of curve numbers. And so you'd say, I want my precipitation to start at maybe 1 inch and start value at 1. The minimum would be 0.5. The maximum would be 3 inches. And the standard deviation 0.25. And so it would come up with a normal distribution of precipitation values, and it's random. It's just going to pick a variety of random precipitation depths, and you could specify a range of curve numbers, and it would fill in a random selection of them, and then it would run the model at all of these different distributions, and you'd see like what's the upper range and the lower range of runoff likely to be out of the watershed area. Well, that's all the time we have for today. Remember that you've got a homework assignment related to WMS that's due on Thursday of next week. No, the week after Thanksgiving. Thursday of next week. Your assignment is to eat lots of turkey. But the assignment of the Thursday after that is not to eat lots of turkey. It's to turn in the homework, the WMS homework. So hopefully you've gained some comfort and familiarity with it. If you got any questions on WMS, let me know. But I won't see you on Thursday. You'll watch that video that I gave you the link to, and then we'll have a quiz the Tuesday after Thanksgiving covering that video.